Hi, in this video, we're going to take a look at supervised learning with gradient boosting. All right, so gradient boosting is an ensemble method that usually uses tree models. All right, so what we're going to do is I'm going to build a decision tree. Then I'm going to take a look at how that decision tree did. And I'm going to build a new decision tree to address the mistakes the first one made. Now, I'm going to take the first two. I'm going to look at how they perform together, and then I'm going to look at where the mistakes are, where the errors are. And I'm going to make a new tree that addresses the mistakes of the first two. And then I'm going to look at the performance of all three together. And I'm going to make a new tree to address the mistakes of the previous three. And I'm going to keep doing this over and over and over, maybe hundreds of times until I finally get a model I like in the end. And this is the typical approach of gradient boosting. All right, well, you would think about it, well, if I'm going to be, looking at my errors, make a model for the errors, make a model for the errors, make a model for the errors over and over and over, we would be super prone to overfitting. But what we're going to do with this is that when I go through and I build those new trees subsequently, I'm going to do two things. First, I'm going to make sure that that tree doesn't get very deep. That's going to prevent overfitting on its own. But wait, there's more. What we're going to do, we're going to make sure that each tree afterwards doesn't have as much input on the overall model as the previous ones. And so we have two mechanisms of protecting ourselves from overfitting. Now, something I've talked about with tree models is that you can think of the different ensemble approaches as being kind of like Goldilocks. All right, so when I do random forest, I let the trees go very, very deep. And in fact, each individual tree is too deep and they end up all averaging out. And then with gradient boosting, I'm going to make my trees very shallow because of the fact that I'm trying to, engineer it to correct mistakes to protect myself from overfitting. I make my trees too shallow. All right, so random forest, individual trees are too deep. Gradient boosting trees, individual trees are too shallow. They're not deep enough. And then regular old straight decision trees are just right. So we're dealing with like a Goldilocks problem. Okay, so let's go ahead and dig into it. All right, so we're going to be using scikit-learn. Scikit-learn has two major approaches for gradient boosting. There's also one that's a histogram approach that is in another video. Here we're going off of the two that are probably more common to be used. They're more well known. I've the very first model where I work at that I took over for somebody else was a gradient boosting regressor model, because that was the most accurate model that they had when they worked on the project. And I've refreshed that model since then, but the project is still going because it's been successful. So we've got, for classification, we got gradient boosting classifier, and for regression, we have gradient boosting regressor. These models both use boosting. Boosting is where you build a model, take a look at performance in some way, shape, or form, build a new model to address shortcomings, and repeat that over and over and over. Most of the time, boosting is done with trees, but technically it doesn't have to. Bagging is where we combine models where we don't consider like previous performance. In boosting, every model that I look at, I have to consider the previous models to be able to get a full interpretation. In bagging, each individual model stands on its own. This is an ensemble approach. All right, so the gradient boosting overview. So we're going to be building our models sequentially, and each new model attempts to correct the errors made from the previous models. And when I say previous models, I mean as a ensemble together. These models are combined to produce a final strong model. All right, so we're going to initialize a model using just a constant value, and then we're going to iteratively fit base learners so that when I say base learner, that's a very simple model on its own to reduce the errors of the combined model. So, for us, simple means a decision tree that is very shallow, that does not go deep, and is not going to go as deep as a proper decision tree. So the key idea of minimizing the loss function is by adding new models that reduce the errors of all of the previous models put together. And so each time I build a model, I'm correcting the errors of all the ones as an ensemble had before it. And we do this iteratively. Now, I also talked about reducing the influence that previous or that subsequent models have in the ensemble. You'll notice that here I'm going to take the previous models that I have. So as I do things iteratively, this is my current one. This F sub n minus 1 is the current model that I have. I'm going to correct the errors. The one that's going to correct the errors is this H sub m. Now, to prevent overfitting, I'm not going to give the current model as much influence as the previous models as I built. And this is the learning rate parameter, this gamma sub m that I have here. And so that's how I'm going to make sure in a second manner, I'm going to protect myself from overfitting. Now, the gradient boosting classifier, here we're just going to be a little bit more specific on what we just talked about a moment ago. The overview is correct, but now let's talk about the details a little bit more precise. So when we have the gradient boosting classifier, we're going to minimize the logistic loss function. That's the default setting. There are other loss functions that we can use. Scikit-learn is just changing a parameter, easy peasy lemon squeezy. I typically don't worry about changing the loss function unless there's a specific desire for my project that I'm working on. So I'm going to initialize the model with a constant value, and then, for binary classification, this could be the log odds of the positive class. And then I'm going to iterate the M base learners. And when I say base learners, remember that's shallow decision trees. Then we're going to compute the residuals for the current ensemble model that I have. And then I'm going to build a new base learner to correct those residuals. So I'm trying to correct the errors on every single way. Now, notice that I'm basing it off of the residuals of all of the previous models thus far. And because of that, when I look at an individual decision tree, I can't just interpret it directly. I have to consider all other models that came before it to get the full interpretation. This realistically, most situations, this isn't feasible. And this is an aspect of why I personally prefer random forest over this, but this is a darn good, darn accurate approach. So, I've used it plenty of times at work, and I'm going to continue to use it. I have a bias. I prefer random forest, but you know what? I've used this plenty of times, and it has delivered for me every time that I've picked it. And then I'm going to update my model. And notice I've got the learning rate parameter right there coming into effect. Now for gradient boosting regression, it's a similar story, but now I'm going to be using, like an error aspect. So like probably mean squared error that I'm trying to minimize, or possibly mean absolute error. Mean squared error is better for the purpose of avoiding big mistakes. So one thing I've learned the hard way is that trying to reduce your overall error is not the best choice, because that would be reducing mean absolute error. It's easy to talk about. You can say, oh, here's the average error when I talk to my stakeholders, but it's mean squared error that, because it squares the mistake, the mean squared error does a better job as a loss function of avoiding big mistakes. And honestly, at work, it's more important to avoid big mistakes than it is to get it right. It's something just from life that I've learned the hard way. All right, so we're going to start with a constant model, and it's just going to be the overall average. Keep it simple. Then I'm going to iterate, or I'm going to build my first base learner, and then I'm going to compute the residuals, and then I'm going to build a new base learning model to correct the residuals of the previous. And then I'm going to keep on doing this over and over and over until I have my final model. All right, now there are several hyperparameters to consider. Now, if you look at the Scikit-learn's documentation, there's a lot of parameters to work with. These are the ones that, in my opinion, are the most important. Number one, number of estimators. This is the number of trees in the ensemble. Learning rate. So this is learning rate is how much influence does subsequent trees have compared to the ladder trees or the previous trees, the earlier trees. Max depth, how deep will this go? The minimum sample size needed to make a split, the minimum sample size needed to make a leaf. These are, parameters over and over and over you see when you're working in scikit-learn decision tree models for all types of models. These, in my opinion, are the most important ones. Learning rate is a super, super, super important one for the gradient boosting models. All right, so let's go ahead and run through an example. And I'm going to use UC Irvine's heart disease data set. So we've got 76 attributes, and but that were referred to in the experiment, but there's only 14 in this data set. And we've got as a target variable, we have 0, 1, 2, 3, or 4, depending on aspects of heart disease. To make this simpler, I'm just going 0 or not 0. And so I'm going to change this over to a binary classification. If I see a 1, 2, or 3, I'm going to bend that into just the number 1 to make things easier. And so this is help documentation. I just copied and pasted so you can see through it. You can see that we've got a mixture of numeric and categorical data. Now the categorical data is coded as integers. And so this is something I have to consider. I don't want to just take categorical, non-ordinal categorical data and just drop it in as is. I need to convert that over to another type of data. I need to get dummy variables going. In scikit-learn, we always need to have numeric predictor variables across the board. Scikit-learn will not accept other types of data, so I'm going to need to convert this over. Now, the ones that are binary, even though they're categorical, if they're binary and they're coded as 0 and 1, I just leave them alone. If they're coded as 0, 1, 2, 3, 4, 5, 6, whatever, then I'm going to convert those over to categorical data and use dummy variables. All right, so let's go ahead and get the data. So you'll notice that I can pull this directly very nicely. I don't have to actually have the data set in on my machine. And here I'm going to assign the column names. And in this data set, a question mark means missing value for us. All right, and so here we can see the head of things. So you notice that sex is 0 or 1, even though sex is not a numeric data type. I can go through and look at these and see that that we've got values that are coded as integers when they're categorical. And for my target variable, notice I've got this 2 here. I'm going to convert 2, 3, 4 into 1s in a moment. And now here, just to get a better feel for what's going on as I work through my project, I am looking at averages. I'm looking at ranges, distinct values. Notice that sex is 0 and 1. FBS is also 0 and 1. The binary categorical variables, I can just leave those alone. I don't have to mess with them. Very nice. All right, so here, quick and easy, I am converting my target variable to 0s and 1s. So if it's 0, leave it alone. If it's not 0, make it a 1. Now I'm going to partition my data into train, validation, and test using random choice from NumPy. And now let's talk about the missing values. There are 2 columns that have missing values in this data set, CA and FAL. And so I'm just going to be using the mode, the most frequent observations, to fill it in. At work, I would actually go through and do a full missing value analysis, to check and see what's the best call. But here for this video, I just want fast, quick, and easy. So filling in 0, filling in 3. Now the numeric data, any time I have a tree model, monotonic transformations of numeric data will not improve or degrade model performance. And so I don't really need to fuss with it. So I'm just going to leave those alone for this. This is one of the reasons why I like tree models so much, because I don't have to fuss with data prep. If I want a quick, fast model, the tree models, the ensemble models are a good choice. All right, so sex, FBS, and XANG are binary columns. I'm just going to leave them as is. I'm not even going to use get dummies on them. But CP, REST, ECG are categorical coded as integers and need to be converted to dummy variables. And so here one thing I always do at work professionally is I like to have my category. I group all my predictor variables by like their data type and how I'm going to do my data prep. So I'll have my numerics in one list. I'll have my binary in one list. I'll have categorical in another, ordinal in another, just to get things going. Text columns will be in another list. And just like I have here, I just have the names in a list, all nice and neat for me to work with. All right, and so you can see that these three are binary. I don't need to do anything with them, but CP, REST, ECG, slope, and thou, these are coded as integers even though they're categorical. And so I just need to drop these in to get dummies, convert these over, and so now here are what the column names are of these four after I do the get dummies, after I've done the one hot encoding, I've converted over to dummy variables. All right, so now, so here is my X. This is my train, validation, and my test predictor variables across the board, the entire data set. Here is my target variable. And now I'm going to specify the training for my predictors and training for my targets. All right, so now I'm going to do parameter tuning. I like grid search. I know people talk about other techniques. I still, for my projects, I haven't really seen other techniques really outperform, grid search. Yeah, I've seen advantages, slight. I like just knowing that I've picked up everything, and when I find like a good region of values, I can go deeper and like keep tuning as much as I want. For learning rate, the default is 0.1. My coworkers have said to me that they feel like this is too large of a default value. By the way, this actually came up during a peer review of a model that I put in production. That 0.1 was, in the reviewer's opinion, was too large. It's the default value, but whatever. So expect to just use a smaller value than that. For this video, you can see that I'm running over a whole range of values. Putting in a 1 is effectively not reducing the influence of subsequent models after the previous. And now here we also have the number of estimators. The default is 100. All right, so we're going to do grid search. Here is the learning rate values I'm going to try. 0 means that future trees have no influence. Here's the number of estimators. Now, a good place to start, anytime you're modeling, if you don't know what to do for things to try, take default value, take half, and take double. And that's a good place to start. And then start looking, where, if you're completely lost, don't know what to do, good place to start. And then start looking around and, of the value you get. So here, if I did half, did default, and did double, 3 by 3, I would get 9 different models in my parameter tuning. Whichever of the 9 gave me the best results, start parameter tuning closer to like that pair that gave me the best. And now here I'm going to set up a data frame just of all the different values. So here I'm setting up all the possible learning rates, all the possible number of estimators, and I'm putting it into a data frame so that it's just all nice and neat and clean for me to work with. So here, this is equivalent of doing expand.grid in R. All right, now what I'm going to do, I'm going to go through down that data frame, and for each of the values in the data frame, I'm going to store the model, and I'm going to have a model there. I'm going to fit the model. Then I'm going to check its performance. And so here I'm just saying, hey, I'm creating a column of just models that have not been fitted yet. I'm just running over the grid of values I have here. On this step, I'm fitting the models. Notice that I'm using list comprehension to keep things all nice and neat and match them up to my data frame columns. And now I'm going to get the actual predicted values. All right, so now when I do this, I'm going to go through and just compute the AUC of each of these models on my train, validation, and test sets. And after I do that, so here I'm getting the AUC. You can see that I'm doing it over the train, validation, and test, and I'm doing it for each individual model that I have. So, quite a bit of work happening here, but it's pretty fast, pretty quick. Now let's visualize the performance. And so what this can do, the intention of this is to show a grid where I have number of estimators along the x-axis, the learning rate here, and then I can plot the AUC of 0.5 is, solid red. A perfect AUC is a very, very dark green. And we can see this one should be train. This one, yeah. I believe, yeah, this one will be, it'll be train, validation, and test. We can see that, we have a lot of dark green on here. We can see immediately that a learning rate of 0 gives us a crap model no matter what's happening. So that's just picking up the very first, the very first tree that's built is the only one that has influence. So it's not surprising that we don't get something very good here. All right, so now let's do validation. And now you can see it's a little bit lighter. Remember, the validation set is a holdout set. But we still see plenty of dark green. So practically speaking, we have a lot of good models that we could use. And now let's do it on our test set. And the validation and test are very, very similar to each other off of this. We have a lot of dark green. All right, so now which model do I want to use? I want to use the one that is simplest. Well, I define simplest in my way as being first of all, using the fewest trees is what I'm going to want. So what I'm going to take all the models that have a test AUC greater than 0.99, validation greater than 0.99, and then train greater than 0.99. So I can see that I've just got, these are, so far it looks like these models are going to perform very well. I still haven't isolated it down. Remember that I did a pretty large parameter search grid. So I've got a lot of models to consider. There's plenty of these to have to wade through. All right, so now let's go ahead and let's select the one of all of these models. Practically speaking, they're giving me all the same, test, validation, and train statistics. And remember, I always check my train statistic compared to validation and test to double check to make sure I'm not overfitting. All right, so we narrowed it down to, over 200 models. It's still, a good amount. At this point, my AUCs across my partitions is not giving me, further information. They're all so tight, I really can't distinguish between these. All right, so what I'm going to do, I'm going to pick the one that has the smallest estimator, and then I'll go with the smallest learning rate because I want to nail it as early as possible. And so here we're going to have N estimators of 50 and then a learning rate of 0.2. So this is comparatively a pretty simple model. This one here has 200 decision trees and has no shrinkage going on. And so I feel much better using this one. All right, now feature importance. All right, so something that's going to come up if you're actually building a model at, putting into production at a large organization. Something that your stakeholders are going to want to know is which variables are the most important? Which ones do we need to focus on? Because that helps them just understand the model. That helps them understand their business process as they work on their stuff. And this is also a good way to double check to make sure, hey, is this a good model? because if you get feature importance that doesn't make sense to your stakeholders, either they have bad subject matter knowledge, which in my opinion has happened to me at work, or your model is crap. And that's happened to me at work also. And so, this at least gives me a double check. If feature importance makes sense to my stakeholders, then I'm more prone to say, hey, I have a good model. Let's progress forward in the project. All right, so how feature importance is computed is through an impurity reduction aspect. And so something about this is that this is looking at the purity of the predictions. It's not looking at the purity of the actual performance of the model. And so when we look at variable importance, it's not looking at it from in terms of improvement in accuracy. It's looking at it as do I have a more pure, more constant value? So we're think of it as we are reducing variance of predictions. We are not considering accuracy of predictions when we do this. And so we have the Gini impurity here for classification. There are others that we could use, but I believe this is the default one. This is the one that I lean on the most, or reduction in variance within a leaf. The mean squared error. Not mean squared error, but it's deviation from the average. And we can also do a weighted version. There are tons and tons and tons of ways to go about variable importance, but generally speaking, this is a good way to look at it. Now, also we can we're going to be aggregating over across all trees, and so we'll have to take into consideration the importance of each tree, in the shrinkage, and we need to take into consideration just how much of an improvement did it get. Now, something that will also happen is that we're going to make the feature importance interpretable. It's always going to add up to 1 in scikit-learn. And so that way we just have, we can just kind of interpret like what's most important in this. Now, when we look at variable importance for any tree model, including gradient boosting, there are times that we'll have a rare event that is a big deal, but it will get a lower importance than it really should have in the tree-based model. And so, for example, let's talk about bankruptcy. When we have bankruptcy, it's a rare event, but if we're talking about something like collections or credit or something like that, bankruptcy is rare, but when it happens, it's a big, big deal. So if I'm talking about collections, I want to identify who should be chased after for collections for not paying. If I see that the customer has a bankruptcy, I probably shouldn't worry about them, but tree models will tend to tree models will tend to give less importance to rare events that are a big deal than they really should. If I look at generalized linear models will give a rare event like this a very, very big coefficient. But when I look at the tree model, it's going to be shrunk down because it doesn't have enough opportunity to really come to bear in this model structure. So just be aware of that. Make sure you understand that as you go through. And so to get the feature importance, I almost always put this into a data frame, and then that sets things up very nicely for me to be able to sort what's going on. Now, if you go in and you get feature importance out of a scikit-learn model, it's almost always going to be feature importances underscore, at least on the version of scikit-learn on my machine. There are previous versions of scikit-learn that will leave it as feature importances, and feature importances underscore. And you can have problems with those slight differences because Python just doesn't like to be backwards compatible, just that way. So what I'll do, I will put everything very nicely into a data frame. You'll notice that here, this is the numeric values, feature importances gives you the numeric values doesn't tell you the name of the feature itself. You have to go to feature names in to get that. All right. And so now I've got the predictor variable. I have its features importance, and I'm sorted from largest to smallest. And now here I take the cumulative sum. One thing that you will notice most of the time is that we'll have the Pareto effect when we're doing a tree model, in that 20% of our predictor variables will account for approximately 80% of the importance. That's normal. That's to be expected. If I want to do backwards elimination, I'm going to go and I'll remove the ones that have the lowest importance first, unless I have like subject matter knowledge that says, hey, this is important, keep it in there, or if I have stakeholders that want it in there. I've come into the experience where I have a very low importance predictor variable. I want to get rid of it. Stakeholder wants it in there because they believe it's important. I'm putting that bad boy in there because I need to make sure at all times my stakeholders have faith in my work. If they don't have faith in my work, there's no point in me doing this project. I would rather produce a weaker model that gets used than a strong model that gets chucked in the bin. All right, and so just to prove to you that feature importance is rescaled to 1, I'm just adding them all up so you can see that. And now I'm going to go through and just do a bar plot so you can see what it typically looks like when we have the feature importance of a tree model. Now, another use of random forest and gradient boosting models is to detect interactions for the purpose of generalized linear models. All right, so something that is a pain in the neck when I have a lot of predictor variables and I'm using logistic regression, SOM regression, multiple linear regression, something like that, is that I need to go through and figure out who should I have for interactions. Well, it works out that gradient boosting and random forest do a good job of picking up interactions. Now, they do a good job of picking it up, giving us good prediction values, but there's a catch. It doesn't tell us which variables have interactions together at all. It doesn't tell us the degree, doesn't tell us if we should have squares or anything like that. It just, under the hood, it picks up the effect, but it gives us no indication of what there are. So what we can do, though, is I can take a model. So let's say I firmly believe that my gradient boosting model has picked up interaction effects for me. What I could do is I could look at the predictions across a grid of values and then check to see, hey, does it look like I need to have an interaction going on? All right, so the more the contour plot does not look like parallel straight lines, the more the plot indicates that there is an interaction between the two. Now, this approach heavily depends on the model actually detecting interactions. So realize that we are not actually using the data to detect this. We are using the model's predictions to detect the interactions off of this. And so if the model didn't do a good job picking up the interactions, it's not going to help us. It's not going to, we're going to get junk output. All right, so if I have parallel straight lines, that's an indication I don't need an interaction between those two distinct predictor variables. If I have contour lines that look like hyperbolas, think y equals 1 over x, but it can be tilted and rotated around. If it looks like, y equals 1 over x, if I tilt my head or upside down or rotate, flip, anything like that, then that's a very strong evidence that I want to include an interaction term. If you ever don't know, you're unsure of what the extremes are, just apply a contour of z equals x plus y, no interactions in this one, and then plot z equals x plus y plus x times y. Here I have an interaction effect, and you'll see it looks like a y equals 1 over x, but like in a different manner. I'll show you in a second. Now, when we use this technique with the gradient boosting models, this is copy and pasted from the help documentation. The punchline of this is that I want to use the brute method instead of the recursion method. Recursion is not what I want. I want brute if I'm using gradient boosting model. Honestly, brute works for all model structures, but it's computationally intensive. So you have to make a decision on that. If you have a lot of data, if it's going to take a long time, you might want to use recursion. I think, you know, if computation time is not an issue, you should use brute forcing it. All right, so here's an example of when we would not want to have an interaction term. You can see that the contour lines are all parallel to each other. And notice that the color aspect indicates what is the target variable values. Now here, look at this, that part and this part. That looks a lot like 1 over x is equal to y. And here, now, you know, it's shifted over, it's not quite exactly that. Don't worry about that. Look at the overall shape. If it looks like a hyperbola, and this is a hyperbola, then that is strong, strong, strong evidence that I want an interaction. And so these are like polar opposite extremes. Here, this is strong evidence of don't use an interaction. This is strong evidence of use an interaction. And so I want to consider an interaction anytime the contour plots do not look like parallel lines. And the more they look like hyperbolas, the more I want to consider an interaction. And so here, to go through and plot this using scikit-learn, I'm going to use partial dependency display, use from estimator. The estimator is the model that I've already fit. So I'm making the assumption at this point that this model picked up interaction effects in its predictions. If it did not, then I'm doing junk data science. And I need to specify the data that I'm going to use when I do the predictions, and I need to specify which columns are involved. And so these are going to be numbers to go across the columns of this data set. And you notice I'm using brute on there, and there are a few errors that come up. I just, you know, almost always at work, I skip over errors and then go back after and see what happened, where, you know, what's missing. All right, so first we're going to look at the case of a single. There we go. All right, so here I am considering, this is stupid data science, but this is a good baseline to look at. I'm considering age as a interaction with age. So age interaction with itself. So I'm considering a square. So I'm not actually looking at the interaction between any distinct predictor variables. But you see that here it's parallel, 100% parallel. If this looked like something that would look like a quadratic term, if this looked like level sets of averaging across the contours of a parabola, then that would be indication of what I would want. So if I saw like purple, yellow, purple, or yellow, purple, yellow, then that would be indication of having a degree 2 term for a linear model. So when I'm doing this, when I'm going through this process here, I'm not actually going to be using a gradient boosting model. I'm not going to be using a random forest model. I'm going to be using a generalized linear model, and I'm using this other modeling structure to detect where do I have interactions that I want to consider in the generalized linear model. I could also use stat models to do hypothesis testing, but you know, repeated hypothesis testing has problems. I prefer the visualization approach. All right, so now here, you know, we've got all these plots. It's going to be a subjective decision on what to go with. But the more it looks like parallel lines, and the parallel could be straight up, horizontal, slanted, whatever it is, the more it looks like parallel lines, the less I'm going to consider an interaction. The more it looks like a hyperbola, the more I'm going to consider an interaction term. And so, you just scroll through when to make the judgment call on each of these. I can't really tell you. You kind of just have to use this and, like hypothesis testing, subject matter knowledge, and decide what looks best. We can use these. So these are individual plots for the variable to make a decision on, is there something meaningful? If I see a flat line, that's an indication that I don't want to include the predictor variable in my model, at least as a main effect. Like here, this is an indication I wouldn't want resting ECG1 in my model. All right, well, there's tons and tons of these to wade through. If I was on a real project, I would do that, but I'm not, so I'm going to go ahead and stop. All right, so gradient boosting models. My experience is that they're very, very accurate. They're reliable. I don't like them as much for interpreting individual trees, but this is a very, very good way to model. If you don't know, this will probably pick up effects that you want. We can also use this for detecting interactions for a generalized linear model, multiple linear regression, Poisson regression, Tweedy, logistic regression, any of those types of models. So, this is powerful. This is useful. This is a standard tool and a data scientist tool belt. All right. Well, that's all I've got for you. Life is short. Do math.